12.4 Lesson 1 Tangent Vectors Objectives. You'll be able to find the unit tangent vector to a curve at a point. So one of our vocabulary terms for today is unit tangent vector. You'll be able to write a set of parametric equations to represent a tangent line to a curve through a point on the curve. So another vocabulary term today is tangent line to a curve. Let's begin with an activity for Objective 1. So what we'd like to do with this particular activity is sketch the graph of this vector-valued function, find r prime of t. That I can do very quickly. R prime of t is, the derivative of t is 1, so I have 1i, and the derivative of t squared is 2t, so I have 2tj. That's r prime of t. So we want to sketch the vector r of 1 in standard position. This is what we call the position vector. We'd like to begin this activity by sketching the graph of our vector-valued function r of t is equal to ti plus t squared j. So I made this table, and each of these are vectors, and when I sketch the vectors in standard position, the terminal points of the vectors will trace a curve in a particular orientation. The terminal points of the vectors in standard position will be at negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. And because the increasing values of t are going from left to right, the orientation of the curve is from left to right. So the next part of the activity is asking, sketch the vector-valued function. We've already done that, so that's what I have here. Find r prime of t. We've already done that. R prime of t is 1i plus 2tj. Now draw r of 1 in standard position. So r of 1 is the vector 1, 1. And I want to draw that in standard position. Let's draw that using a different color like gold. So that would be the vector r of 1. And you can see that the terminal side of the vector is a point on our curve. Draw r prime of 1 such that the initial point is at the terminal point of r of 1. So what is r prime of 1? So if I want to find r prime of 1, I will evaluate my vector-valued function r prime of t at t is equal to 1. So 2 times 1 is 2, and I will have 1i plus 2j. And I want to draw r of 1, I want to draw r prime of 1, 1i plus 2j. I want to draw r prime of 1, the vector 1i plus 2j, such that its initial point is at the terminal point of r of 1. So here's r of 1, here's the terminal point of r of 1, and I want to draw the vector r prime of 1, 1i plus 2j, so that it starts here at the terminal point of the vector r of 1. So starting here, go 1 unit to the right and 2 units up. This is what I have for the vector r prime of 1. And then it says find the magnitude of the vector r prime of 1. Well, here's the vector r prime of 1. How do I find its magnitude? So the magnitude is found using the formula for magnitude. And I have the square root of 1 squared plus 2 squared. So that would be the square root of 5. So that tells me the length of this blue vector. So what is the unit tangent vector? Definition of unit tangent vector. Let C be a smooth curve represented by r on an open interval I. The unit tangent vector t of t at t is defined to be, what is r prime of t? It is the derivative of the vector valued function r of t, and you're dividing that by this scalar quantity, the magnitude of r prime of t, such that r prime of t is not the zero vector. Let's go back to our activity. Again, for your just to remind you, this was the vector valued function from our activity. We graphed it, and then we sketched the vector valued function r of t, which is the parabola that you see there. We found r prime of t. R prime of t is, of course, easy to find. It is 1i plus 2tj. And we drew r of 1 in standard position. So that was this vector here. And then we drew r prime of 1. So r prime of 1 is 1i plus 2j. We drew r prime of 1 such that its initial point is at the terminal point of r of 1, and that was right here. And you can see visually that the vector r prime of 1 appears tangent to the curve at the point 1, 1, corresponding to t is equal to 1. So that's something that you observe. This particular vector, when drawn as we just did, appears tangent to the curve at the point 1, 1, corresponding to t is equal to 1. And that is not a coincidence, that is in fact the case. So this is called a tangent vector, but here we're defining a unit tangent vector. The difference between a tangent vector and a unit tangent vector is that a unit tangent vector has a magnitude of 1. So how do we make sure that we will get a unit tangent vector? You begin by finding the tangent vector, just like we did for our activity, and then you have to find the magnitude of that tangent vector, just like we did earlier. So the magnitude of the tangent vector is going to be the square root of 1 squared plus 2 squared, or the square root of 5. That's a little bit more than 2. So how do we make this tangent vector have a magnitude of 1? We're going to multiply the vector r prime of 1 by the scalar 1 over the magnitude of r prime of 1. And that is exactly what is stated in this definition of the unit tangent vector. And the purpose for doing that is to have what we call a scalar multiple of the vector r prime of t, such that our scalar multiple of the vector r prime of t will have the magnitude of 1 unit. It will be what we call the unit tangent vector. And that is achieved simply by taking the vector r prime of t and multiplying it by the scalar 1 over the magnitude of r prime of t. So as you can see here, for our particular example, I will find our vector at t is equal to 1. That is the tangent vector. That would be what we have here. And then we will multiply that by 1 over the magnitude of this vector, which is square root of 5, and that would be what I have here. This is called the unit tangent vector to our curve at t is equal to 1. You can also generalize and find the function that would give you the unit tangent vector at a particular value of t. To find the unit tangent vector function for our activity problem, we would simply use this definition, and the unit tangent vector is 1 over the magnitude of r prime of t multiplied by r prime of t, provided that the vector r prime of t is not the 0 vector. So all you have to do is find r prime of t, which is very easy to do. R prime of t is simply 1i plus 2tj. And if you want to divide that by 1 over the magnitude of r prime of t, how do you find the magnitude of this vector r prime of t? You do the square root of the sum of the squares of the individual components. And when you distribute that scalar, you will have the unit tangent vector for the function r of t is equal to t I plus t squared j. And if you evaluate this unit tangent vector at t is equal to 1, you'll get the one that we found earlier for our particular problem, where t was equal to 1. And of course, this was the unit tangent vector that we had found earlier, corresponding to the value of t equal to 1. We just looked at objective 1. You'll be able to find the unit tangent vector to a curve at a point. And now we'll take a look at objective 2. You'll be able to write a set of parametric equations to represent a tangent line to a curve through a point on the curve. Example 2. Find the unit tangent vector function and then find a set of parametric equations for the tangent line to the helix given by r of t is equal to 2 cosine ti plus 2 sine tj plus tk at the point corresponding to t is equal to pi over 4. You'll notice that our vector-valued function is in 3 dimensions. So let's look at the graph of this vector-valued function, the 2-dimensional representation of this 3-dimensional curve. You will make the observation that because the horizontal or the x and the y components are 2 cosine t and 2 sine t, the base, if you were to think of this 3-dimensional curve as being on a 2-dimensional base, the 2-dimensional base would be a circle centered at the origin of the xy plane with a radius of 2 units. And then if you extend that circle into 3 dimensions by either raising it or lowering it, you will get a cylinder. And it is on this cylinder that you see pictured here in the figure that you will have the spiral that is the graph of r prime of t. And that spiral is going to rise for increasing values of t. When t is equal to 0, you will have a point on the xy plane. For positive values of t, you will have points that are above the xy plane, and for negative values of t, you'll have points that are below the xy plane, all the while being on the cylinder that would be the extension of this circle above and below the xy planes. So what that means is the spiral will be on the cylinder as you see pictured here in this diagram. So now what we want to do is we want to find the unit tangent vector. That's easy to do. To find the unit tangent vector, what we're going to do is we're going to find r prime of t and multiply by 1 over the magnitude of r prime of t. So the unit tangent vector is as follows. So r prime of t is simply, let me write the vector in component form. I will differentiate the vector r of t component by component, and that will give me the derivative of cosine is negative sine, so I have negative 2 sine t. The derivative of sine is cosine, so I have 2 cosine t, and the derivative of t is 1. And of course, I need to multiply that by 1 over the magnitude of this vector. What is the magnitude of this vector? So you will have negative 2 sine t squared, which would be 4 sine squared t plus 2 squared cosine squared t, which would be 4 cosine squared t, plus the square of 1, which is 1. And then you can factor out 4 from the first two terms in the radicand, and you will have 4 times sine squared t plus cosine squared t plus 1. And of course, sine squared t plus cosine squared t is 1, so you'll have the square root of 4 plus 1, which is the square root of 5. So that's the magnitude of the vector r prime of t. And using that and this definition, I can find the unit tangent vector to our curve. You'll notice that in this problem, the magnitude of r prime of t does not depend on t. It is in fact a constant. So this is our unit tangent vector. And what does it tell us? It tells us where we will have a unit vector that is tangent to our curve at different points on the curve given by different values of t. The unit tangent vector is also helpful because it tells us the direction in which a particular curve is heading at a particular point in time. So it is especially useful if you want to think of this as velocity, because after all, what is this? It is the derivative of the vector valued function r of t, and when you take the derivative of a position function, if you have a particle that's moving along a path described by r of t, if you take the derivative of the position function, you of course get the velocity function. So the unit tangent vector t of t will tell you the direction in which the curve is being traced at a particular point in time, whether you have the unit tangent vector or you just have the tangent vector. Both will give you the same direction. And in fact, these coefficients are called the direction numbers. They act much the same way slope would act in a two-dimensional plane. These numbers tell you the direction of a particular line in the XYZ space. How can we use that to do what we're being asked to do in example 2? Find the unit tangent vector, we've already done that, and then find a set of parametric equations for the tangent line to the helix given by this vector valued function at the point corresponding to t is equal to pi over 4. So you can see here what point we're talking about. You can evaluate the vector valued function r of t at t is equal to pi over 4. So you have 2 times cosine of pi over 4 I plus 2 times sine of pi over 4 j plus pi over 4 k. Where on the curve is this point? Cosine of pi over 4 is square root of 2 over 2, so it is at square root of 2i plus square root of 2j plus pi over 4k. In other words, you need to go from the origin, positive square root of 2 units along the x-axis, positive square root of 2 units along the y-axis, and pi over 4 units along the k-axis to find the point. So here's the x-axis, here's the y-axis, and here's the z-axis. I meant to say the z-axis here. So you're going to go square root of 2 units along the positive x-axis, square root of 2 units along the positive y-axis, and pi over 4 along the k-axis. That gives you this point here. So if you want to write a set of parametric equations for this tangent line to the helix given by the vector valued function r prime of t at the point corresponding to pi over 4, it is perhaps surprisingly easy. And here's what we're going to do. We're going to rely on the coordinates of the point, which are right here. I will go ahead and circle that in green. These are the coordinates of the point. And then we're going to rely on the direction numbers, which here have been circled in gold. And here's how we're going to write our set of parametric equations for the tangent line to our curve at the point corresponding to t is equal to pi over 4. Since we're in 3 dimensions, we'll have 3 equations, one for x, one for y, and one for z. And the easiest way to do this is just to say, what is the x coordinate of the point of tangency? Well, it's square root of 2. What is the y coordinate of the point of tangency? It's square root of 2. What is the z coordinate of the point of tangency? It's pi over 4. And then we're going to choose a parameter that is not so far used in the problem. So we have t already used, so I don't want to use t. I want to choose a different parameter that has not already been used in the problem. So I'll choose, say, the parameter s. And s would represent a certain amount of change. Maybe it's a change in time, whatever s may represent. It doesn't really matter. But what you're going to do is you're going to say, from the point of tangency, in which direction is the curve going to be traced? Well, it's going to be traced in these directions. First of all, I would like to make a correction as far as the direction numbers go. You would have to evaluate your unit tangent vector at the particular value of t that gives you your point of tangency. And that particular value is, of course, pi over 4. So when you do that, you get 1 over square root of 5. And for each of the 3 components, you will have sine of pi over 4, which is square root of 2 over 2, giving you negative square root of 2. And then you'll have 2 times cosine of pi over 4, which is square root of 2 over 2, giving you positive square root of 2, and then you'll have 1. When I said earlier that these were the direction numbers, I actually meant after that particular vector was evaluated at t is equal to pi over 4. So with those direction numbers, you're basically going to say, I start with my point at the point of tangency, and for each unit of the parameter s, how much am I going to change in the x direction? How much am I going to, in which direction am I going to go with respect to x? In which direction am I going to go with respect to y? And in which direction am I going to go with respect to z? These are the directions that I'm going to go, because these are my direction numbers, and these numbers act much the same way as slope does in 2 dimensions. And one important thing to note here is if you let s be equal to 0, you don't add anything to the coordinates of the point of tangency, so you'll just get the point of tangency. But of course, if you let x be, for example, 1, you'll be further along the tangent line to the curve at the point t is equal to pi over 4. So this is how you write a set of parametric equations for the tangent line to a curve at a point. So today we looked at finding the unit tangent vector to a curve at a point and writing a set of parametric equations to represent a tangent line to a curve through a point on the curve. And we used vocabulary such as unit tangent vector and tangent line to a curve.